Hey everybody, this is a review video going over the sample test that I posted on MyOpenMath. Um, let's let's start off by just talking about the generalities of the test. This is the final exam announcement at the top of the MyOpenMath page. July 7th, this coming Monday. You can start anywhere from 9 a.m. to 5 p.m. It is the odd hours that they want people to start on. So if you, well, I'll be explicit. 9, 11, 1, 3, and 5 are the times we'd like people to start. That makes the sessions last 2 hours. Nobody's going to be checking how long you're there for. So if you need more than 2 hours for the test, that's perfectly fine. Just try not to disturb other people that are in the session while you're coming and going. The announcement includes a couple of statements that we should talk over. First of all, the exam is comprehensive. I have a sample exam posted here, and this is the format our test will take. There'll be a first portion where you're not allowed to have a calculator or a cell phone app. So just you still get to have a sheet of notes, but that's the only thing the only aid you'll have present. Once you finish with that, you turn it into the proctors and show them, if you're starting up, say, GeoGebra, show them that you're doing that and putting it into exam mode. And you also need to make sure to be able to show the proctors the final splash screen when you're quitting from exam mode. So, but basically, first part of the exam is no calculators allowed. There are kinds of things you ought to be able to answer without the aid of a calculator. And the second part where it's fine to use them. You may not need them for everything, but you're certainly permitted to use them anyway on the second portion. All right, so let us get going. That is this rather old exam. Oh, I think I'll probably mention this twice at some point. I'll say another thing about this, but this exam is so old that it's actually missing a few topics. In particular, the Leontief models and the linear programming portion. We'll only look at, on the exam, we'll only have linear programming using the graphical approach. So, well, I'll provide you with some additional sample questions to cover those materials. But let's get started with what is here. The first problem shows us a graph of a function. Looks like some sort of cubic function, but you'll notice it has a hole in it right there. So when x is equal to 2, the point above that is missing. What is asked about on this guy is four things. And you'll notice they come in pairs. We've got a limit and a function value. And both of these are happening at 2. The limit as x goes to 2, and then the functional value at 2. And then we've also got another one that's a limit and a functional value. This is happening at 1. F of 1, and the limit as x goes to 1 of f of x. So can we answer those questions by looking at the graph? Let's take the easier one first, which is the latter piece, the limit and the function value as x goes to 1. Well, that is what is sometimes called an ordinary point on the graph. Nothing funny is going on there. There's no discontinuity. There's nothing like this hole, this point that's been plucked out of the graph. It's just regular. And in that situation, if you have a continuous function passing through a point and defined at that point, you're fine. The value of the function, the limit, they both agree. What is the value here when x is 1? It's 0. And so the limit as we approach from the left or from the right, it's also 0. So I can fill in those two pieces rather quickly. 0 and 0. There we put equal signs. The things that are happening at 2 are a little different. The value of the function is simply, well, it doesn't have one, so we just write undefined in that situation. When you've got something like that, where no point on the graph lies right above 2. The limit, however, on this one is okay, because except for right there at the point 2, we've got something that looks like almost a line going through that point. What is the x and y coordinates of that missing point? Both of them are 2's. X is 2 and y is 2. So the limiting value as we approach from the left would be 2, or as we approach from the right, also 2. Cool. The limit exists, and it is 2, but the value is undefined. Moving on, problem number 2 has us do some simple derivative calculations. There's sort of 3 factoids you need to know for these, all 3 of these guys. One is the so-called power rule, which says if you have a variable to a power and you're taking the derivative of that, what you do is bring the exponent there out front and you change it to 1 smaller in the exponent. X to the n's derivative is n times x to the n minus 1. So that's one piece that you should know. The other things I hope are clear to people. If you have constants, their derivatives are 0. And if you have something that's just a multiple of x, the derivative of that is simply whatever the multiplier is. So if I have a multiple of x, and I prime that, I'm just going to get m. And if I have a constant, like the b that you see in a linear equation, that's 0. So those 3 things are ones to keep in mind as we go through these things. The first one is 3x minus 1. Maybe there's a 4th thing that I should mention. When you're taking the derivative of a sum or a difference, you just work on the pieces individually and add and subtract them as indicated. So we've got a multiple of x. The derivative of that is just the multiple. And then a minus 1, which is a constant. That's the derivative of 0. So we're done. The derivative of that thing is 3. Next one, x cubed minus 1,000. Well, x cubed really needs this power rule thingy, right? And we'll take the 3 out front and reduce the exponent to a 2. The minus 1,000, that's a subtraction of a constant, so it's gone. You don't have to do that either. The last one doesn't have a constant, but it does have a whole lot of things added up. We just need to differentiate each one of them separately. 5x to the 4 plus 4x cubed plus 3x squared plus 2x plus... this one might trick you if you think it doesn't seem to have a multiplier on it, but it kind of does. There's a 1 that you could think of as sitting there by default. So that's what we get. You could also go look, what is the slope of the line y equals x? That's a line at like a 45-degree angle, and it has slope 1. So there's a couple of ways to think through that. Problem 3 has us, we did one like this. In fact, I fear this may actually be the same one that we had on our last exam. You've got a drawing of a function, doesn't tell you what the formula is, and it just wants you to estimate what the derivative looks like. There's a pretty quick procedure you can follow in cases like this, which is locate where the graph has local minima and maxima. These places where a better way to think of it, the good way to think of it is the tangent line is 0. It has a slope of 0 right there. So at those 3 points, the tangent line is horizontal, and that means the derivative at those x values is 0. So wherever you see a max or a min on the function, you can say, okay, the derivative is going to be 0 at those x coordinates. So I've got myself 3 points where I know the derivative is 0. The other thing you want to do is look at the behavior of the function, whether it's increasing or decreasing. If it's going downhill, and this is as we travel left to right, downhill means it's decreasing or the slope is negative. That means the derivative is negative. So like right in here, we would have negative values for the derivative. But you see between this low spot and this high spot, we're increasing. That means our derivative will be positive in there. Then with another piece where it's decreasing, that's negative. And finally, a nice, looks like an infinite chunk where it's increasing and going up quite a lot. Okay, so how do we finish out the graph? I think I'm going to switch colors. Oh, red is already what I got. Can I do it in black? Where the graph, the little signs I wrote tells me I want negative. I want to draw something underneath the x-axis, below the x-axis. Where it's positive, we should head up, be above the x-axis. There's a positive chunk in there, but it's zero at either end of this interval, so something like that. And finally negative that way. Yeah, that's may not be perfect, but it's a pretty good approximation of what the derivative looks like. It did say in the directions, indicate the places where your estimate of f prime of x is zero. I think that's fine the way I've drawn them in dark there. The graph will get pretty crowded if you try to point at each one of those things and say f prime equals zero. So I would certainly accept that. All right. Okay, our next problem asks us to do some derivatives that are not quite as straightforward as that first batch. And I want to talk to you about some things that should definitely be on your crib sheets. The three standard rules for differentiation. So one is the product rule, where you're multiplying two functions, and you want the prime of that product. That's, fancy name, product rule. It looks like, actually, I sometimes prefer to write that down in a way that doesn't have the of x's on everything. And it's just quicker. So you could say f times g prime is f prime times g plus f times g prime. A little less confusing looking, in my opinion, when you don't have to say what all the of x's are. Unfortunately, with the next rule, the chain rule, I can't do that because, it's got, it's important to know where things are evaluated. In the chain rule, we're looking at the composition. Sometimes I would call f the outer function and g the inner function. You should notice, just as a mnemonic device, that what we're seeing here looks like literally the product of f prime and g prime. The only weirdness is that they're evaluated in different places. G prime is evaluated at x, and f prime has g of x as its argument. Well, that corresponds with what f and g had in their arguments as in the question part of this thing. So g was evaluated at x. That's why g prime is evaluated at x. F was evaluated at g of x, and that's why f prime gets evaluated at g of x. So for a lot of folks, that's the most confusing of these rules, but it's not bad if you see it that way. It's just the product of f's derivative and g's derivative, with the place they're evaluated matching the place where the original functions were evaluated. Finally, the quotient rule. This is usually the hardest one to memorize, so I really suggest don't memorize it. Put it on your crib sheet. I just need to point out, though, that to get it right, let me come back to the product rule for a second. F prime g plus f g prime, that could have been done in the other order, and it would have been fine because we're adding in between those guys. But in the quotient rule, we're subtracting. So you really do need to get the order correct. And it's this one, f prime times g minus f times g prime. You really have to have the prime on f in the first one, f being the numerator, and the prime on the denominator in the second one. And then, essentially it looks like the product rule with the plus turned into a minus, and then this extra bit of dividing by the square of the denominator. All right, so let's try to use those guys in solving these problems. The first one is clearly a product. I hope everybody sees that. And so I will have let me write it out as sort of directions of what to do. We want to differentiate x squared and then times that by e to the x, plus then we want to leave x squared alone and differentiate e to the x. But both of those are derivatives that we know how to take. X squared is 2x. So we'll have 2x times e to the x. And then this is another one of these things that I'm hoping everybody has encountered at this point. E to the x is kind of unique amongst functions in that when you differentiate it, it just doesn't change. It's the same function when you take its derivative. So you get 2x times e to the x plus x squared times e to the x. I find a lot of folks, just because of the way you've been trained by your algebra teachers and up to this point, want to simplify that. Let me argue that you should not simplify it. You should just leave it the way it is, because it looks right now like it came out of the product rule. So it's more obvious to me that you've done the right thing when you leave it looking like a product rule. This guy, if you don't recognize it at first, let me say it's a composition. The seventh power is done on the outside, and we've got this polynomial on the inside. So this is like our f of x is x to the 7, and g of x is, well, let me write all that crap out, x cubed plus x squared plus x plus 1. All right, so what's the derivative of the seventh power? It's 7 times its argument to the 6th power. I'm just going to write that by leaving a little bit of a space to fill in its argument later. Well, I guess now later is now. Remember that f's derivative gets evaluated at the same place f was evaluated. So this has got that polynomial x cubed plus x squared plus x plus 1 on the inside of it. But that's not the whole story. We also, that's just f prime evaluated at g of x. We also need to have g prime of x. And you need parentheses to make that right. If you don't put the parentheses in, it would just multiply the first term of the derivative. Anyway, 3x squared is the derivative of x cubed. X squared becomes 2x. And x becomes 1, and the 1 on the end is a constant, so that's derivative is 0. We're done. All right, again, I think I'm going to write it out as instructions of what to do first. We want the derivative of x squared plus 1 times the bottom, which is just x, minus x squared plus 1 without a prime on it, times the derivative of the bottom, x prime. And that will be all divided by the bottom squared. I may not have left myself quite enough room to sneak this in, so let me try to do it. X squared plus 1's derivative is 2x. So 2x times x minus x squared plus 1 times, what's the derivative of x? 1. Yeah, so we have just minus x squared plus 1. I better put parentheses around that so I get the, we should be subtracting that 1 as well as the x squared. And then we would have x squared in the bottom. Now, this sort of looks like it simplifies a lot, and it does, but I still recommend don't do the simplification. Just leave it like that, because it looks like somebody applied the quotient rule, and that's what we wanted. This next question covers a topic that we haven't really dealt with in the class, but I'm going to go ahead and say a few words about this. It's the second derivative. What does the second derivative mean, and what does it do for us? So maybe I could do some miming for you here. I'm going to jump back to a view of me. If I have a function that is sloped downhill, right, and then its slope changes from down to up, its first derivative went from a negative value to a positive value, right? So what is happening in terms of increasing or decreasing on the derivative if it's going from a negative number to a positive number? Going from small to big, that means it's an increasing thing. So when f prime is increasing, we get a graph that looks like that. Did I do that in the right direction for you guys? I may be doing a mirror image thing. This way to that way. Yeah, hoping I'm doing that right. Well, anyway, if you see the shape of that, it's curving in a sort of a smiley face way. If the first derivative is increasing, that means the derivative of the derivative, f double prime, is what? The derivative is increasing. Well, just think of the derivative as being the function. If the derivative is increasing, then the derivative of the derivative is positive. So a positive second derivative tells you you've got a curve that looks like a smile. And that means if you've got a flat spot at the bottom of it, it's a minimum. So this is a test that's often used. You're not going to see a question like this on the art exam, but I still thought it was worth it to show it to you. So let me go back to this and we'll see it. What is f prime on this graph? F prime of x is x squared minus 2x plus 5. The derivative is 2x minus 2. And then if I took the derivative of that, getting f double prime of x, you see that you'll just get 2. Cool. So this first one, the derivative itself, you notice that it's 0 when x is 1. So that means that x equals 1 is a critical point. I'm just abbreviating the heck out of that so we can fit it in. X equals 1 is a critical point, and the second derivative is positive. That's the other piece we're noticing. F double prime is greater than 0, because it's actually the number 2. It's always just the number 2. It doesn't have any x in it, which means what? Any low spots on this graph are going to be minima. This graph has a smiley shape to it. You might even be able to work your way through plotting that thing. And it wouldn't be that hard to come up with a plot by hand of it. But this isn't stuff that either of these derivatives are things that you would really need a calculator for. So what was the final question in this thing? Use the second derivative to determine whether f of x is concave up. That's just terminology for smiling, or concave down, which would be frowning. And that's these two shapes, okay? Concave up and concave down. And in our case, it's up. Concave up. Not concave down. And does that mean we have a minimum or a maximum at this critical number? Well, we have a minimum. So I'm just circling the answers on that, just to give you an idea of what it looks like. Kind of a cool topic, but we're not doing it, so don't worry too much about that. All right, number 6 on our sample test, the first part sample test, has a whole bunch of matrices. And notice that, I really don't expect everybody to do matrix algebra by hand most of the time. You do not need to do the operations. See how it says, do not, really loud, compute any of them. Just tell me which ones could be computed. And that is all based on the size of the matrices involved. So let's just jot down underneath of these things how big they are. That one has 2 rows and 2 columns. So when you say a 2 by 2 or a 2 by 3, you're always mentioning the number of rows first and then the number of columns. For this one, that makes a difference. That's a 2 by 3 matrix. This one is a 3 by 4, 3 rows and 4 columns. Another 2 by 2, 2 by 2 right here. What the heck is that one? 4 by 2. 4 rows, 2 columns. And the last one is 2 by 3. Cool. Now, which ones can be done, and it says you should just circle the ones that you could compute. The things that are sums, or they could be differences, those things can only be done if the matrices have identical sizes. They have to have exactly the same number of rows and columns. So could we do A plus B? No. One's 2 by 2 and the other's 2 by 3. Would we do A plus C? Really no, because 3 by 4 is pretty far from 2 by 2. How about A plus D? Yeah, that's a good one. A and D are both 2 by 2 matrices. B plus D? That's a 2 by 3 and a 2 by 2. Different sizes. B and E. Nah. 4 by 2, 2 by 3, those don't match exactly. B and F. Oh, look, yeah, those two are the same. They're both 2 by 3. So those are sort of the easy questions, whether you can add or subtract matrices. They have to have identical sizes. When you have to multiply matrices, what you need is the length of the rows in the first matrix is equal to the length of the columns in the second matrix. Some people just say this is a case of matching what are known as inside dimensions. So if I have A times B, for instance, A would be a 2 by 2 matrix, and B would be a 2 by 3 matrix in this with the values that are given there. And the two numbers that have to match are those ones, the ones that are closest to one another in that little notation I've written down. So they do match, and that means A times B is doable. We can compute that. A times C, let me just point at the things. We got a 2 by 2 and a 3 by 4. The inside dimensions would be 2 and 3, and those don't match, so nope, can't do it. A and D are both 2 by 2, so that's doable. B and C, that's 2 by 3 times 3 by 4. Weirdly, those 3's match, and so that can be done. I should tell you the other numbers that are involved there, the 2 and the 4 in this one, tell you how big the product will be. So when you multiply this 2 by 3 times this 3 by 4, you'll get a 2 by 4 answer. What else? C times E, that is a 3 by 4 times a 4 by 2. The 4's are the inner dimensions, and they match. And how about F times C? Can we do that one? Yes, it would be a 2 by 3 times a 3 by 4. The 3's are the matching inside dimensions. So many of those products can be done, but not all of them. All right, this is a linear system thing. We don't need to graph it because it's graphed it for us. And mostly this question is just about following whether you understand the terminology. A consistent system is one that doesn't have any internal inconsistencies, right? Situations that just mean you can't solve that. So this is a system that is not consistent, because is it ever going to be the case that those two lines intersect somewhere? Is there some point which is on both of those lines? Not when those lines are, quite obviously parallel to each other. So quick answer here, it's inconsistent. When would it be consistent? There's actually two cases. The lines could be parallel but identical. They could lie right on top of one another, and that's perfectly fine. It's still consistent. Or the much more normal or usual situation is the lines end up being non-parallel and they cross each other somewhere. But anyway, that case where you've got lines of the same slope that don't have the same y-intercept is inconsistent. Looks like we're doing more matrix stuff, but again, do not solve the system. Just wants you to, well, what does it want you to do? Write the system of equations represented by the following augmented matrix. That's a piece of terminology you should have seen. Augmented means that it's really got a kind of dividing line between the matrix that are the coefficients of the variables and the right-hand sides of the equations. But yeah, this is just asking us to use x, y, and z as the variables and turn what these rows of the matrix into equations. So the first row is x plus 3y minus z is equal to 7. The next row doesn't have an x, but it has a twice y plus 4z, and that's equal to 8. And the last row has all the variables. X and y are added, and then z is subtracted, and that will equal 5. I have to always cross my z's because it's just the way I write. I make them look a little too close to 2's, so I'll try to be careful about that. Yeah, that's the whole issue on this. Just can you, and I could see another problem that you might arise where you're given the system like this as a set of equations. Could you write down the matrices? It's pretty straightforward to do, but either way. Last problem on this set, or on this first part of the thing, is a linear program issue. It asks us, again, don't do the work, don't solve it, but set it up, which is, in my view, that's kind of the human element. You use computer packages to actually solve linear programs, but determining what's the objective function and what are the constraints and such, that's requires a human being to kind of understand the actual setting of the problem. And maybe ChatGPT will get around to doing this soon, but I'm going to give that a test and find out. Anyway, what do we got? Bob is making trail mix. He's got a regular sort that has 12 ounces of granola and 4 ounces of raisins, and he makes $1.25 off of selling a pound of that. He's also got a premium one that has a little bit less granola, 10 ounces, and 6 ounces of raisins. So I guess it's more raisins make it premium. And he makes $1.50 from each pound of premium he sells. He's got some constraints. He's got a certain amount, 40 pounds, which I'm thankful they gave us the conversion into ounces here, 640 ounces of granola and 480 ounces of raisins. So those are the constraining conditions. He's going to make up some number of bags of each, and he wants to make the most money off of this. I would say first, we ought to recognize that this is a maximization problem. So we want to maximize an objective function. The maximization problem here is we're maximizing profit. Now, P is, well, $1.25 for each pound of regular and $1.50 for each pound of premium. Notice in the last paragraph here, it tells us to use X for the number of pounds of regular and Y for the number of pounds of premium. So it'll be X times 1.25 plus Y times 1.50. And then there are constraints, which we are going to need to write down. The first pair of constraints you should always mention are non-negativity. This is almost always the case, that you want to have your variables represent positive quantities. So X is greater than or equal to 0, and Y is greater than or equal to 0. There are rarely cases where you might have negative values for some of your constraint variables, but not often. And then what else? Well, the ingredients to these two kinds of granola is what give us some inequalities that have to be respected. If I think about the raisins, for instance, I have 4 times X, 4 ounces of raisins in a pound of regular, and 6 times Y, it's the amount of raisins that are in a pound of the premium stuff. What was the limit on how many raisins are available? 480 ounces. So that gives us this inequality. Sorry, that 8 is rather ugly. 4x plus 6y is less than or equal to 480. The other issue is the granola. Let's see, he has 640, I'm pointing at it, but it's off screen. 640 ounces of granola. On the left-hand side is going to be that number. Why did I just say left hand when it's the right hand? I don't know. The upper limit on something is the number of ounces of granola we have. And we need to multiply X and Y by how many ounces of granola each type requires. It was 10 ounces for the, No, it wasn't. It was 12. Good, because those don't add up to 16. There's 16 ounces in a pound. I know. Can you guys tell that that's a 12 right now? I'm going to scribble it out and just start again. 12x plus, what about the y? Y had, that was the premium sort, 10 ounces of granola. So 12x plus 10y is less than or equal to 640. That's a reasonably easy problem to actually solve, but again, it told us not to. So, don't spend time on stuff that you're not required to do. Look for indications like that. Don't solve it, and respect it. All right. So that's the end of the first part. We're going to be using GeoGebra on the second piece a bit more. Maybe not for the first one. Actually, yeah, I guess I'll go ahead and do it for all of them, even though, some of these things you can solve by hand. Yeah, so a little reminiscent of something we had on exam one. A tank of fuel oil contains 40,000 gallons of oil. At time equals 0, a pump is turned on, and that can suck 800 gallons of oil out of the tank per hour. I'm noticing the word removes there, so I wanted to emphasize that by saying it sucks it out. It's coming away. That means it's a negative rate. So you can probably quickly write down the formula for the capacity, or what's in the tank. It's 40,000 minus 800 times T. Cool. That is the answer to this part where it says give an equation for the amount of oil remaining in the tank as a function of time. The second thing it asks is when will the tank be empty? And that would be, let's call this formula A of T. A for amount, I guess. Anyway, what it's asking us to figure out is at what time does A of T equal 0? Right, that's the question. Let me write out that formula equals to 0 and see what it lends us to. We have 40,000 minus 800T equals 0. If you just add 800T to both sides, you get this equation. 40,000 equals 800T. And finally solve for T by division. So T is 40,000 divided by 800, which I can probably do just by covering up two zeros. And 400 divided by 8, that's 200 divided by 4, 100 divided by 2. I think that's 50. I could certainly verify that with a calculator. Let's pop over to a GeoGebra window and try to verify that, using the calculator. So what we had was the formula for the tank's capacity, or tank's actual content at time t was 40,000 minus 800 times t. I'm going to use x as the variable because that'll make better sense to the system, because it's going to try to plot this thing. You will notice that it hasn't plotted anything. Well, the problem is we got to zoom way out, and there it looks like we're getting a vertical line. The problem is the slope of this line is negative 800, so it's a very steep line. The pump is quite powerful. I'm going to try to get on there and change the y scale without changing the x scale until we see that it's, if you get the axes scaled appropriately, you can definitely see it's a line with a y-intercept of 40,000 and a slope of minus 800. And so what we were after is just that value, right? The root of the equation, or that's another term for the zero of the equation, is at 50, which is indeed what I had worked out. All right, back to looking at the test. here's the next question on part 2. Find the equation of a line in slope-intercept form that goes through the point 5, 7 and has a slope of 1/2. Well, you should know the point slope form. Y minus the y coordinate of your point is equal to our slope, which in this case is 1/2, times x minus the x coordinate of the point, which is 5. And so that's cool if you can write that down, but that is not what it asked for. It asked for slope-intercept form. And another piece of terminology you just need to know. What does slope-intercept form mean? That's the one that most people think of as kind of the most usual form. It's the mx plus b version. So when you see slope-intercept, it's mx and b. And this doesn't look like that, but we can certainly do a little algebra and turn it into that. What would we need to do? Let's multiply that half through. So y minus 7 equals 1/2 times x minus 5/2. Let's add 7 to both sides. So y is 1/2 times x minus 5/2 plus 7. And I should be able to combine, those constants. Minus 5/2 plus 7 is, well, let's write it as a decimal. It's 4.5. You could certainly pull out a calculator if you need to for this one. So we can do it by algebra, by hand, but we can also do this on a calculator. So let's pull that game. Guess I don't need that thing anymore. Get it out of here. So look, our equation is going to look like y equals 1/2 times x plus, whoops, got to use my arrow key to get out of the bottom of the fraction. 1/2 times x plus some y-intercept, b. Okay. At the current scale, we don't even see that line. Let me go back to, you see this home view thing? It also takes you to the standard view. Something's wrong. It didn't give me a slider for b. How about we say k? Oh, I know. I'm thinking about how Desmos works, not how GeoGebra works. We need to make a value, a slider for b. I don't know. How about minus 10 to 10 with an increment of 5? We can leave the rest of the things at the default settings. Really? It just needs to have numbers there, apparently. I don't know what speed means. How about we give it a 1? Width, I think that's in pixels, so 100. I think I'm going to try something else here. I think I really don't need those. I can just go, oh, good. Yeah, so that's a confusing thing. When you give a slider, you really only have to specify min, max, and the increment. But I was awkward with using the thing, so you do have to delete the rest of the arguments list on that thing. But there's a lot of stuff you can see here. So if what I've got is b equals 2 and y equals b plus 1/2 times x. Why am I not seeing the graph? Oh, there it is. Well, what else do I need to make this all work out for me is the point that we were supposed to be going through, which is x is 5, y is 7. So I'm going to put in 5 comma 7 as a point. There it is. And I just need to adjust b until we get our line to go through that sucker. That wasn't so bad. B, well, apparently it's 4.5. So you can see the I don't know. I feel like that's more work than just doing the algebra, but I feel like I also need to show it to you. So let's see if we can get back to that document camera view. Uh, all right. We do have some logarithms here. It's not necessary to use a calculator on these particular ones. Maybe I'll throw in a few more where you would need a calculator. But these guys are actually, in all cases, what we're looking to take the logarithm of is a power of our base. Let me start here at the bottom. The base is 5. Do you recognize 25 as being the square of 5? Well, that means this logarithm is the power, 2. And log base 3 of 27, the question is, what power of 3 gives us 27? That is 3. And how about this guy? What power of 10 gives us this number? Well, for powers of 10, you just have to count how many zeros. I'm seeing 5. So those can all be answered without using a calculator. But if you want to, I guess we should check it. I could just ask for instance, log of 10. How many zeros was there on that? 5? There, I feel silly doing this, but yeah, it gives us a 5 there. If you type log and you see the options here, one of the options is logarithm with a base on it. So let's select that guy. And the base 3, the function, the place we're evaluating 27, what does that give us? It's 3. That's funny that it didn't just calculate log 3 of 27. If you notice before I hit go on that, it wrote it as ln of 27 over ln of 3. That's the change of base formula. What was the last one we had? Log, we want to, this one, logarithm telling me what the base is. Logarithm base 5 of 25. And of course, that's going to give us a 2. I have to hit the approximation button. It's not really approximate, it is exactly 2, but yeah. I feel like the system has it confused, which is the approximate and which is the accurate answer on this one. Anyway, back to our problems. We're about to try. Sorry. We're about to try the next one. Now, this is an application of the exponential growth stuff, and you will be using logarithms at some point in any kind of application of exponential growths. Well, maybe not all the time, but if you get one of these kind of questions, how much time will elapse before you reach a known amount? That's going to be requiring logarithms. Okay, so let me read this to you, and then we'll attempt to solve it. Yeast is added to a vat of grape juice in order to ferment it to make wine. The amount of yeast present in the vat doubles every 4 hours after it is added. I think that's a little fast, but you know, sometimes we like to use nice round numbers for math questions. So, okay, suppose 5 grams of yeast is added to the vat at t equals 0. Oh, sweet. They give us a formula. A formula for the amount of yeast at time t is A of t is 5 times 2 to the t over 4. Well, now, part of that makes good sense. The 2 to a power is because the yeast is doubling every so often. Why is it t over 4? Well, it's because of the 4 hours being how long it takes to double. So if you divide your time by 4, you find out how many 4-hour increments have happened. And that is what the doubling time is about. All right, so we started with 5. That's the other piece of this. The 5 out front is how much we began with, the initial value. So answering this first part is really just plugging in A of 5. Plugging in 5 for t in that, and it'll be 5. Sorry, I just said it wrong. How much yeast will be present in 24 hours? That's not 5, it's 24. There. Well, it was 5 out front. Maybe that's how my brain got confused there. 5 times 2 raised to the 24 over 4. I'm not sure. I just put in a set of parentheses that really aren't required because you would do the exponents before you did the multiplying. But anyway, 24 over 4 you can do in your head probably. That's 6. So we have 5 times 2 to the 6. 2 to the 6 is 2, 4, 8, 16, 32, and one more, 64. So this is 5 times 64, or what is that, 320. I believe that is another instance of me borrowing a question from this sample to give you on your exam too. We had that same answer previously. I'm going to have to make sure I give you all new problems for the final, or at least change some of the numbers, huh? Anyway, how much time will elapse before the amount of yeast reaches 500 grams? For that, you should write down that the output is 500 and just copy in the formula for the amount, which is 2 to the t over 4 here. 5 times 2 to the t over 4. All right, so we need to get that t, which is in the exponent, out of the exponent so we can solve for it. That's what logarithms are for. My advice is to first divide by 5. That just makes your life a good bit simpler. 100 equals 2 to the t over 4. You have your choice of what logarithm you would like to use, but there's 2 obvious candidates. Because the base is 2, a logarithm base 2 would make sense. But this number being a 100, a round power of 10, means common logarithm makes some sense too. I'm going to make that choice. Take the logarithm of that side, and you will just get 2. Let's just write down what the log of the... I accidentally made that lag. Log of 2 to the t over 4 is. So I just want that to look like I've applied the log to both sides. But there is a rule with logarithms that when you have a power inside the logarithm, you can pull it out and it becomes a multiplication factor. So this is 2 equals t over 4 times log of 2. Now, everything on the page, the 2, the 4 that we're dividing by, and the log of 2, those are just all numbers. And so you can treat them as numbers and then solve for t. I would suggest don't actually calculate what the log of 2 is until you've solved for t, and then you'll get full accuracy out of the calculator. Whereas if you say, oh, this is about 0.69, then you'll be rounding to two significant digits, and that is probably not what you want. All right, so t is, if I solve for this t, I'm going to times both sides by 4. So I'll have 4 times 2, and I'll need to divide both sides by log of 2. And I certainly want to get a calculator to do that. I'm going to clear all this other stuff out for a moment. I don't need to save it. What was the thing I was trying to calculate? 2 times 4 divided by log of 2. You may be concerned about the way it's written that, but this is the same as 2 times 4 in the top divided by log of 2 in the bottom. And again, it's written it in terms of natural log, and that's okay, I guess. Wait. Oh, I see what it did. It doesn't matter. Get the value. Get GeoGebra to tell you what the number is. And I would say it'd be silly to round this to give any higher accuracy than 1 decimal place. So 26.6 is our final answer. That would be in hours. Yay. Okay, so problem 5 in part 2 of our sample test. We've got a function that's given by a cubic polynomial, and there's also a restriction on the domain. We only have the graph between -3 and 4. Well, to find the critical numbers, though, we don't need to worry about that. They're just places where is the derivative 0. So let's just write that now. We want to, well, where is f prime equal to 0? Well, in order to solve that, we have to know what f prime is. So let me get it. F prime, take the derivative of 2x cubed, and that would be 6x squared. 3x squared becomes 6x. And then minus 12x becomes minus 12. There is no, the 1 doesn't matter, right? Because you take the derivative of a constant and get 0. You should notice that there's a 6 in every term there, so we can factor that out. And you end up with x squared plus x minus 2. Well, I can tell you that factors. I'm not sure why I know that so well, but it does. This is 6 times x plus something times x minus something. Why do I know one thing is plus and one thing is minus? Because the last times last give us this negative number, minus 2. And that's interesting. If it's negative 2, it's either 1 times minus 2 or 2 times minus 1. Which is it? Well, the outer times outer and inner times inner add up to plus x. So I think we want the plus 1 to be the bigger of those two numbers. Did I just figure it out right? Well, you can always do these factoring things by guess and check. I guessed, what is the product of these two things? Yeah, I definitely get the minus 2 on the end. 2x minus x from the outer and inner terms gets me the x. Yes, x squared is certainly the first times first. So that factored form lets you know what the critical numbers are, because that's sort of the purpose of doing the factoring. X is minus 2 or plus 1. There's our critical numbers. Now look, the phrasing here is important. This asks for the absolute minimum and maximum, and that's not the same as just find the relative min and max that happen at these critical numbers. The absolute minimum and maximum, you have to figure out what's the biggest overall and what's the smallest overall, and that includes this stuff. There's a limitation on x values, so it might happen that as we get to the endpoints, we're at a bigger or a smaller value than we are at either of the critical numbers. It really would be smart for us to take a look at the graph on this, right? All right, so I'm going to need to illustrate how to create a graph that has limits on the domain. So what we want is a function that is controlled by a condition. And in GeoGebra, you type if, and there's more than one form of it, but the condition we want is that x lies between minus 3 and 4. So we just go ahead and put in that inequality that f spans or is in the range between minus 3 and 4. And then, well, that's the formula, which we had, what was it, 2x to the third plus 3x to the second minus 12x plus 1. That was our formula. So if you plot that, well, I'm going to need to scale things a little bit here. Let's scale the vertical axis so that we see more of the graph. You see the limits, well, you see the left limit anyway. Yeah, there we go. The right limit just appeared on here too. And then f at minus 3, 10. There we go. What else do we need? We need f's value at the critical numbers were minus 2 and then plus 1. You can see those are places where the tangent line are horizontal. All right, so f at minus 2 is 21. F at 1 plus 1, negative 6. And f at 4. That's the right-hand endpoint, 129. So what's the biggest of these? Definitely it's the 129. What's the smallest? The -6 we're seeing right there. Let me return to our written version of things. The absolute minimum was -6. The absolute maximum was 129. You could interpret the last question here two ways. One is give me the points where the absolute extreme values happen. I personally feel like it's enough to just say what's the x coordinates where those things happen. Well, what were they? The -6, the min happened when we were at one of the critical numbers. It was at x equal 1, and the max happened at x equals 4, the right-hand endpoint of our interval. Cool. All right, next. Wow, we might not need a calculator for this. I'm going to do it both ways, but let's see if we can just see whether those numbers work in both of these equations. If x is 10 and y is -1, what is x plus y? It is 9. 10 minus 1 is 9. Well, this is a little harder. If x is 10, that's 20, and then we'd be minusing 5 times -1. There were two minus signs in that, so it's 20 plus 5, sure, 25. So the answer clearly is true. How could we do that with the calculator? First, let's clear everything. The two equations we had were 2x minus 5y is 25. That's one of them. And x plus y equals 9. That's the other one. And yeah, you can see where they cross. Where do they cross? Well, I can't seem to click on it. Usually I think it gives me the chance to click on it and get the intersection, but I'm pretty sure that's 10 comma -1. Yep, that's what it is, all right. So, yes, the answer true is correct on that thing. This first one where we have to actually do some work with a system of equations. I'm again going to show you this both in the calculator and by hand. So this is problem 7 in the second half of the sample. What I'm going to do is the method of elimination. You see the minus x here. If I only had this equation having a -3x in it there, then when I added these things, it would cancel. You can make that happen by just multiplying that whole equation by 3. So we get -3x plus 6y equals 6, if I did that. And now if I add, I get 4y plus 6y, that's 10y. And 24 and 6 is 30. Oh, cool. Well, that's quick. Y is 3, isn't it? So we eliminated a variable. First had to scale this second equation up by a factor of 3, but then when we added it, it killed off the variable x, and we were able to solve for y then. Once we've done that, we should go back to something and figure out, do we want to use that first equation, the original second equation, or the modified version of the second equation? Kind of doesn't matter. You can use whatever one you want. I'm going to go ahead and use the first one. It's 3 times x plus 4 times y, but y is 3, is equal to 24. 4 times 3 is 12, so if I subtract that from both sides, I end up with 3x equals 12. And so finally, x is 4. So y equals 3, x equals 4. The GeoGebra approach to that is to basically plot both lines. Let's clear out this stuff and start with a fresh screen. So we had two lines. Oops, I want to make this a little bigger so you can see it. Yes, 3x plus 4y. 3x plus 4y is equal to 24. That was one equation. It's just barely visible on the screen over there. And then the other one was minus x plus 2y. And the right-hand side of that was 2. Okay. And they do indeed. This time it shows the intersection. I don't know what I was doing wrong before. But yeah, x is 4, y is 3. That's what we just had a second ago. Okie doke. Onward. Our next guy is asking us to compute a matrix product. Now, maybe before we do that, we should verify that you really can do a matrix product with these two guys. One is a 2 by 2 and the other is a 2 by 2. The inside dimensions are both 2's, so these are conformable matrices. The product is possible. I like to put little indicators in to draw something into the matrices so that I do the proper thing on the two things, which is we're supposed to be doing the rows of this matrix combined with the columns of the second one. So I just put a little horizontal divider between those guys and a little vertical divider between those guys. It'll help. The numbers we're going to put in are you multiply corresponding entries and then add. So we'll keep a running total of what we get when we multiply, and then we'll add the next pair of things. Let me first write it out, although I do kind of recommend that you do practice this enough that you get handy with doing it kind of in your head. But the 1, 1 position would be from the first row times the first column, and that's 3 times 2 plus 2 times 1. If we do the first row times the second column, that's the 1, 2 position in our answer. And that'll be, what was it, 3 times minus 3 plus 2 times 1. No, I see. The second row with the first column, we get minus 1 times 2 plus 4 times 1. And the second row with the second column, that's minus 1 times minus 3 plus 4 times 1 again. Now, I wrote those out, but really we should probably have done the computation in our head. 3 times 2 plus 2 times 1, that's 6 plus 2. Sure, that's 8. What was the next one? 3 times minus 3 plus 2 times 1. That's this guy. Minus 3 plus 2 is minus 7. The 2, 1 position. Minus 1 times 2 plus 4 times 1. Minus 2 plus 4 is 2. And our last times last, we get 2 negatives there. Minus 1 times minus 3. So 3 plus 4. 3 and 4 is 7. All right, so if you are worried about doing it by hand or afraid you can't get that computation right, you can certainly use GeoGebra for this. I would just write in a little note if you don't, well, no, it wouldn't hurt to say something like use GeoGebra while you're doing this. So what does GeoGebra do for us here? It lets you make up matrices and then do things like multiply them, or in a minute we'll find a reduced row echelon form. That's me. Oops. Make that bigger. I think I want the font to be a little bigger so you can see better what I'm doing. We're going to create a matrix, and the way that's done is by creating a list of lists. A big list which in it contains a list which is the rows. So our first matrix first row was 3, 2. So we'll have like that. And then the second row was -1, 4. Whoops. That has to be a list, so curly braces. -1, 4. Once you hit enter on that, it converts it to a prettier form. It looks like a matrix now, but if you click on this thing, you can go and edit those entries if you mess something up. We're good, but the other matrix, B, the rows, and while in B we were going to multiply using the columns of it, you still enter it using rows. So a list of lists, the first list is 2, -3. That is the first row of it. And then the second row of it was 2 1s, 1 and 1. Okay. And we can multiply them. A times B. That sounds familiar, doesn't it? 8 minus 7 to 7. I believe that's what we did there. I should point out to you while we've got those entered into the thing that you can do the product the other way around. And it's instructive to see that what? It doesn't work out. It doesn't have the same result if you do if you get the order wrong. So yeah, watch out for this phenomenon. Matrix multiplication is not commutative. You're so used to A times B equals B times A, but in this world, it's not the case. We verified that, right? Okay. This is our last problem on the sample test. It asks us just to find a reduced row echelon form of this is an augmented matrix, I would guess. So what we find is actually the solution to a linear system if we did that. But what's the operations we're allowed to use? Hopefully you followed that section on reduced row echelon form and Gaussian elimination. You're allowed to interchange rows. That's not necessary for this one. You're allowed to scale rows. We might want to do that in this one. And you're allowed to use the row replacement notion. The goal, I'm going to write this up in the corner. The reduced row echelon form of a 2 by 3 matrix like this is going to look like this most of the time. It'll have 1, 0, 0, 1 in the coefficient part, and then in the augmented column there'll be numbers. I don't know what they are. I'm just going to put stars on them so that you'll get the idea of what the shape should look like. So that's your goal in doing row reduction. And you should notice that we're halfway done in this. 1 and 0 are matching with that pattern. We just need to get that to be a 0 and this to be a 1, and then we can do it. Now, so the first thing I'm going to do is a row replacement, where row 2 is going to be replaced with, it always has to include itself so you don't lose the information about itself, but -3 copies of row 1. I'm writing that down because I'm looking here and going, how do I turn that into a 0? I need to subtract 3 of what's above it. So new version of the matrix now. New version. It's an equivalent matrix, a matrix that has the same solution set. The first row, nothing happened to it. The second row, we do this operation in order to create a 0 here. But now we have to figure out what happens to the 2 and the 4. 2, it'll be that value minus 3 of what's in row 1. So 2 minus 0. It's still 2 then. 4 minus 3 of that. 4 minus 6, that's -2. All right, so that's close, but it's not all the way to reduced row echelon form, which should look like this little identity matrix in the coefficient part. 0, 1 is what I want here. What I've got is 0, 2. Can we fix that? You bet. I'm going to scale row 2 by a half. And that makes the final system, final matrix look like 1, 0, 2, 0, 1, -1. Exactly the form that mentioned above, with the stars replaced with 2 and -1. Yeah, but we probably want to see this in GeoGebra as well. Let's clear ourselves out. Okay, so same setup. I want to create the matrix and then ask for its reduced row echelon form. Get the computer to do it for us. So A is a system, a list of lists. That first entry in the, whoops, got too many of them. Let me start that over. I want to, A equals double curly braces. The first row is 1, 0, 2. Make sure to put a comma between that and the next set of curly braces for the second row, which is 3, 2, 4. Okay. 1, 3, 0, 2, 2, 4. That's the correct matrix. The command we were after is called reduced row echelon form. If you start typing, it'll give you a hint about it, and so we want that version of it where we have reduced row echelon form and you supply it with the name of a matrix. And that produces exactly what we got by hand. 1, 0, 2, 0, 1, minus 1. Okay, so I guess that is it for this this little review session. I will be posting a couple of additional sample problems, in particular on the problems of the problem areas of Leontief models and linear programming. They would be things that would be appropriate to have a calculator for.